In an era where, let's face it, power outages feel almost routine now. Thanks to wild weather, grid issues, you know the drill. Having reliable backup power isn't just nice to have anymore, it's really essential preparation. And generators have long been that noisy solution. But if you're shopping now, you'll see two totally different kinds of generators out there.
No.
So our mission today, let's cut through the jargon. We're diving deep into the two main players. The conventional, that's your traditional open frame workhorse, and the newer, slicker inverter type. We want to make sure you really get the differences so you can make the right call for your needs, especially thinking ahead to 2025.
And it really is more than just tech specs, isn't it? It's almost philosophical. The core thing you're deciding, the real hook here, it boils down to what you prioritize. Do you need raw, brute force power, high output? Or is the absolute must-have clean, stable power delivered efficiently? That's the fundamental split. We're going to unpack how both work and why that difference is so critical today, especially with all this sensitive, expensive electronics packed into our homes now.
Okay, right. Let's start with the basics then. Both types, conventional and inverter, they start the same way, fundamentally. They take fuel, gasoline, propane, sometimes diesel, use an engine to burn it, make power. Simple enough. But how that power actually gets refined and sent to the outlets, that's where they completely diverge. Let's start with the older design, the conventional generators, the straightforward ones. Yeah. Engine spins an alternator, and that makes alternating current, AC, directly from the mechanical energy. Now, the key part, to keep that frequency right, 60 hertz in the US, the engine has to run constantly and fast.
That constant speed is absolutely the defining feature. Here, it's locked at 3,600 RPM.
All the time.
All the time.
Regardless of load.
Doesn't matter if you're powering one tiny LED bulb or your big air conditioner. Same high speed. And that constant, fixed, high RPM operation dictates everything else. Since the power frequency is tied directly to that engine speed, well, you get fluctuations. Something heavy kicks on, like your fridge compressor.
Right, big drop.
Yeah, that demand makes the engine dip just for a second. And boom, voltage spike or drop. It's powerful, sure, but it's definitely not precise power.
Okay, so that's the old way. Now, contrast that with the inverter generators. You said they take a more roundabout route.
Much more complex, but yeah, roundabout is a good way to put it. It leads to a far superior result, though. Tell us about that three-step process.
So they also make raw AC first, like the conventional ones?
They do, yes. Starts the same. But then that raw, kind of rough AC immediately goes into a rectifier.
Okay, rectifier.
Yeah.
That converts it to DC, direct current.
Exactly. Think of DC as like a smooth, steady reservoir of power. Much easier to manage. Then, using sophisticated microprocessors, smart electronics, it inverts that nice, smooth DC back into AC. But this time it's stable, clean AC.
Huh. So it's not just making power, it's almost rebuilding it, synthesizing it. Seems like a lot of work just to avoid running at 3,600 RPM constantly.
It is a big engineering step. But the payoff is huge. Efficiency, power quality. It's night and day, because that whole conversion aversion thing, it completely decouples the engine speed from the final output frequency.
So the engine doesn't have to run flat out.
Precisely. The engine becomes smart. It only speeds up or slows down based on the actual power you're drawing at that moment.
And the immediate results are cleaner power.
Less fuel.
Cleaner power, way less fuel wasted, and a huge one for most people, much, much less noise. It's fascinating, really. The designs prioritize totally different things. Precision and finesse for the inverter.
Versus raw power and maybe upfront cost for the conventional.
Exactly. Which brings us back to that critical question you, the listener, need to ask. What specifically are you trying to power with this thing?
Perfect transition. Let's jump into that side-by-side comparison. And let's start with the big one. Power quality. This seems to be the game changer. It really is. The key metric here is something called total harmonic distortion, or THD. This is super important now because THD measures how much the electrical wave deviates from a perfect, smooth sine wave. Inverters, they shine here. They produce clean power, very low THD, usually under 5%.
Less than 5%. And that clean sine wave is safe for?
Everything sensitive.
Yeah. Laptops,
smartphones, smart TVs, Wi-Fi routers, gaming consoles, even complex medical equipment. It's basically grid quality power.
Okay, flip side. The conventional models, because they skip that whole refinement process, they produce dirty power.
That's the term, yeah. The THD can be much higher, sometimes up to 25%.
Whoa, hold on. 25%, that sounds like a lot. Give me a real-world example. What does 25% THD do to my fancy smart fridge compared to, say, an old-school drill?
Perfect question. That old drill. Or a simple work light. They probably won't even notice 25% THD. They use power in a very basic way. But your smart fridge, your computer, anything with microprocessors regulating power. High THD is bad news. It creates extra heat, causes irregular current flow. It can actually damage sensitive circuits over time, shorten the lifespan, maybe even corrupt data.
So that weird buzzing sound you sometimes hear from electronics on generator power, that could be the THD.
Often, yes. It's the sound of those components struggling with that dirty power.
Wow. Okay, so the inverter sounds almost essential if you rely on modern tech during an outage.
For protecting sensitive gear, absolutely. Now, moving on, the next big difference everyone notices immediately is noise and runtime. And they're linked.
Linked back to that variable speed engine again, right?
Correctly. Let's talk noise levels. Inverters are remarkably quiet. We're talking 50 to 60 decibels typically.
Just
Like a normal conversation a few feet away. Plus, when the load is light, the engine slows down even more, making it even quieter.
compare that to the conventionals. 70 to 90 decibels. That's a huge jump. 90 dB is like
standing right next to a lawnmower. Or an old vacuum cleaner running full blast.
Yeah, if you're camping or just trying to be neighborly during an outage, that constant roar from a conventional unit, it's pretty disruptive.
Yeah.
Quiet is a massive quality of life thing.
Huge. And sometimes it's required by local noise rules. Beyond sound, that variable speed directly impacts fuel efficiency. Inverters are generally 20 to 60% more efficient.
60%, that's incredible.
It means longer runtimes. Even a small fuel tank on an inverter might give you 8, 10, maybe 12 hours of clean power.
Whereas the conventional one, always running at that fixed 3,600 RPM, just guzzling fuel.
Right. It burns more fuel just staying ready, so you're looking at shorter runtimes, maybe 4 to 8 hours on a similar tank size. You'll be refueling much more often.
Okay, this is where it gets really interesting for a lot of buyers. The cost, the power output, and portability. That classic triangle, right? Cheap, powerful, portable pick two.
You nailed it. Let's look at raw power output first. This is where conventional generators traditionally win. They are absolute workhorses. Much higher outputs are coming, 5,000 watts, 10,000, even 20,000 watts plus. They're built for heavy loads, running a big central AC, multiple large appliances at once, serious power tools on a job site.
And they have that surge capacity advantage too, right? For starting big motors.
Yes, that's a key point. Surge capacity, that short burst of extra power needed to kickstart things like refrigerator compressors, well pumps, AC units. Conventionals often handle those big initial draws better.
But that power comes at a cost.
Yeah.
Physically, they're big and heavy.
Oh yeah, bulky, often like 100, 200, 300 pounds or more. They're typically meant to be set up in one place, not easily moved around.
Okay, now inverters, lower power generally.
Typically, yes. The common range is more like 1,000 up to maybe 7,000 watts. But their huge advantage is portability.
Right, much lighter.
Definitely. We're talking 40 to 100 pounds for many popular models. Compact designs, built-in handles, much easier for camping, RVs, or just hauling out of the garage when the power guys.
And you mentioned something earlier. If you need more power than one inverter gives.
Yes. Parallel capability. Most modern inverters can be linked together.
How does that work?
You buy a special, usually simple cable kit, connect to identical or compatible inverters, and you effectively double your available wattage.
So you could get, say, 4,000 watts from 2,000 watt units.
Exactly. You get close to the output of a mid-size conventional, but you keep all the inverter benefits, the quiet operation, the clean power. It's a flexible option.
Let's talk dollars and cents then. Cost, return on investment. This is where the conventional models look really tempting up front.
Right. That initial sticker price is definitely lower for conventional generators. You can expect to pay roughly 50% more for an inverter of similar wattage.
So give me some ballpark figures.
Well, good inverters, say in that popular 2,000, 3,000 watt range, might run you anywhere from $500 up to, well, over $2,000 for premium models. Let's say $500 to $3,000 is a common bracket. But then you look at a conventional workhorse like that Generac GP9500E mentioned in the sources, almost 10,000 watts for around $1,000.
Wow, that's a ton of power per dollar initially.
It's incredibly cost-effective upfront if raw wattage is your main goal.
Okay, but you made a strong case earlier for the inverter's long-term ROI because of fuel savings. Let me play devil's advocate, though. Say I live somewhere with very stable power. Maybe I only need backup for 5 hours every, 3 years during a freak storm. Isn't the cheap conventional the obvious choice then, just based on minimizing that upfront cost?
That's a fair point. For the ultra-infrequent user who just needs massive power for a very short duration, very rarely, yes, the conventional probably wins on initial cost. You minimize that sunk investment. However, for anyone who uses their generator even semi-regularly,
like for camping trips, RV power, tailgating.
Or if you live in an area with more frequent, even short, outages, Then the math changes. Fast. Factor in those fuel savings from the inverter, which we said could be $100, maybe $200 a year for a medium-sized unit depending on fuel prices in use.
Okay.
You could potentially recoup that entire initial price difference in just 1 or 2 years of regular use, maybe 3.
So the ROI really favors the inverter for anyone who's not just buying it for absolute worst case, once-a-decade emergencies.
Pretty much. Especially with fuel costs being so unpredictable, that efficiency starts looking really attractive over the lifespan of the generator.
Okay, let's tie this all together then. Connecting it to the bigger picture, the final choice really has to be guided by the specific application, not just the price tag or one feature.
Let's break down those ideal use cases. Where do inverters really shine? Recreation is a big one. Camping, tailgating, anywhere quiet operation is essential, or just, consider it.
Makes sense.
Also, home emergencies, where your priority is running sensitive electronics safely.
Yeah.
Laptops for remote work, routers, TVs, maybe medical devices.
And small businesses needing quiet, reliable power.
Definitely. Food trucks, mobile services, remote work setups. Inverter is often the only practical choice there.
Okay. And the conventional workhorses, where do they still dominate?
Rugged environments. Construction sites needing to power heavy tools, farms running big pumps or equipment, and those large-scale home backups where raw, sustained power is the absolute priority over efficiency or noise.
Like running multiple central AC units during a heat wave or powering a deep well pump.
Exactly. When you need sheer grunt and massive wattage, especially that surge capacity, the conventional models are still hard to beat. They're the heavy lifters.
Beyond power and noise, what about other factors for 2025? Emissions, maintenance.
Good points. Emissions-wise, inverters generally have an edge just because they're more efficient. They burn less fuel per watt-hour produced. So they often meet stricter environmental standards, like CARB in California, more easily.
But manufacturers are addressing this on both sides now, right? With fuel options.
They are. We're seeing a lot more dual fuel and even tri-fuel models in both categories for 2025.
Running on gasoline, propane, sometimes natural gas.
Exactly. Propane especially burns much cleaner than gasoline. So using propane in either type of generator helps reduce emissions significantly. It's a good trend.
What about keeping them running? Maintenance.
It's a bit of a trade-off. Inverters are mechanically simply. In some ways, the engine isn't constantly stressed at max RPM. But if one of those complex electronic components fails the inverter board itself, the rectifier, that can mean specialized, potentially costly repairs. Not always a DIY fix.
Whereas the conventional ones,
they need more frequent basic maintenance oil changes, spark plugs, because they run harder. But the mechanicals are often simpler, maybe easier for someone handy to troubleshoot or repair.
Okay, let's put some real names to these concepts. The sources mention specific examples. A top inverter pick.
The Honda EU2200i is often cited as a benchmark. 2200 starting watts, super quiet, 48 to 57 decibels, really light, only 47 pounds, fuel efficient. But premium price, around $1,100 or so.
That's the gold standard for portable, clean power.
Pretty much. Then on the conventional side, for pure power.
The Generac GP9500E was mentioned.
Right. 9,500 running watts, tri-fuel capability, ideal for running most of a house. And the price is around $1,000.
So, over 4 times the power of that Honda for potentially less money up front. But you're giving up the quiet, the clean THD, the portability, the efficiency.
That's the trade-off in a nutshell.
And a crucial reminder for everyone listening, always, always calculate your actual wattage needs first. Don't guess. And prioritize safety features.
Absolutely critical, especially built-in carbon monoxide detectors, non-negotiable safety feature.
Okay, so wrapping this up, what's the final takeaway here? It really feels like it boils down entirely to your personal priorities, doesn't it? Are you focused on efficiency, quiet operation, portability, and keeping your sensitive tech safe? That points one way. Or are you prioritizing sheer raw power, handling big motor surges, and getting the most watts for your initial dollar? That points the other way.
You've got it. Inverters are clearly dominating for that modern tech-reliant lifestyle, for remote work, for anything portable. Yeah. And that long-term fuel saving is compelling. But conventional generators absolutely remain the champs for heavy-duty, high-wattage tasks, especially if it's infrequent backup for big appliances or tools. Now, here's something to think about moving forward. A final provocative thought for you. We see inverters getting more popular, more efficient. We see conventional models getting cleaner with things like tri-fuel. So how might these hybrid approaches, or maybe future design specifically trying to bridge these two worlds, maybe offering both high surge and clean efficiency, how might those change the game for home power in the next decade?
Could we eventually see one generator that truly does both without major compromises?
It's a really fascinating space to watch. Will technology find a way to give us the best of both worlds seamlessly? We'll have to see.